like, this is an idea that I saw from your work in class. And so, like, yeah, based on the work that you did in class, like, if I said match them and I just gave you the task now, how would you match them? You could draw lines to match them or whatever you'd like to do. So, and we can start with them, like this first one and second one. Go ahead.
I think just like shape.
Yeah, let me label it for you. I'm sorry. So let's label them A, B,
Yeah.
C, D, E. Okay, you're saying that one is, so 1 is E?
No, no, I was gonna say that 5 is A.
That you think 5 is A? I agree. Okay, so we can start there. Why not? Sure. And then there's another shape.
Yeah,
right?
sorry, I don't do it in order normally.
It's okay.
I think 3 is B.
3 is B, you said? And
Yeah.
I agree. So 3 is B. Yep.
Do you want me to like try?
Yeah, sure. You can write.
Okay. I think would 1 go to C?
1 is C, you said?
Yeah.
It looks like it. Let's see. I don't know why I would refute you. Like, yeah, because like you're saying that this is a right angle right here, and therefore this here is a right angle right there, right?
Mm-hmm.
Yeah, I agree with you. So go ahead and draw a line connecting them. Yeah, there you go. Okay, go ahead.
I think that is 6 D.
Is 6 what again? D, you said?
D.
Yeah, I agree. 6 is D. Go ahead.
Like a pretty interesting, weird idea. So the first derivative and the second derivative, I want to plug it into both of them and try to see what happens.
Exactly. That's actually precisely what you should do, because there's no other information that you have, which is you only know that it goes through the point -2, 8, and you have the first derivative and therefore have access to more derivatives. Now, by the way, when it says that this is a differential equation for the function y equals f of x, there are infinitely many functions whose derivative is x squared minus 1/2 y, right?
Yeah.
What's different about them?
That's where we get like the plus c from and all.
Exactly. So there's only one of them that goes through the point -2, 8, and that's what you would use to find that c value. Exactly. Excellent. So, yeah, because you don't know anything else except for the point and its first and second derivative, you have to plug it into the first derivative and the second derivative. But explain to me how that's useful to you. Like, what are you doing with that?
So if the first derivative, so if the second derivative is positive, that means that it's concave up.
That's right.
So like it's weird to explain, but like it'd be like this.
Correct.
Concave up.
Correct.
So if the second derivative is positive, then it's like a minimum. It has to be, because at that point, like
Exactly.
Into the first derivative, so it gives us 0.
Exactly.
Which means that like point in time, right when it like switches, it's like the critical point. So if the second derivative is positive, it has to be a relative minimum, and if the second derivative is negative, it has to be a relative maximum.
Exactly.
Because it's like how the way that the curves work.
Exactly. So in calculus textbooks, they say that this is a second derivative test. It's exactly as you said, which is if you have a horizontal tangent and you're concave down, you have to be a local maximum. And good. So that's that. What about part C?
So part C, this is this is the part that looks actually really difficult.
Yeah.
So let y equals g of x be the particular solution to the given differential equation with g of -1 equal to 2. Oh boy.
Mm-hmm.
Find that limit. Show the word that leads to your answer. So. Oh, okay. Y equals g of x. So that is the. Oh, they give. Oh, okay. So here they want us to actually like do stuff.
Yes.
So. Yeah. We have dy dx equals x squared minus 1/2 y. So we have 1/2 y dy equals x squared dx. So then now we derive this stuff, and
What are you trying to find here?
I'm trying to like separate variables so that I can integrate it, and then I get like a plus c, and then I use the plus c to find my g of x because they give me an initial term.
That's well and good, but here's and that's a great strategy for finding g. But here's my question to you: what if you do all of that and then you end up plugging -1 into g only to find out that it's 2, so you have 2 minus 2 over 0? Like that would have been all.
You know, happen.
Okay, that's funny. Yeah, that's right. Like you wouldn't want that to.
You can ask that.
Yeah, exactly.
Yeah.
So if you were having to if you had to separate the variables and solve, then I think that they would explicitly say find a particular solution and so on. So if the questions are posed this way, then never actually go back and find g, although you had a great plan for finding it. So try to find the limit as it's written because you don't know any better, and see what happens if you try to find the limit as it's written.
It's gonna be 0.
Exactly. So it's gonna be 0 over.
0 over -1 zeros. It's gonna be indeterminate.
Exactly. It's in an indeterminate form. So what do you have to do?
Take the derivative. Oh, alright. Right.
Say that again.
Take the derivative of it.
Exactly.
I can take the derivative.
Are you using the quotient rule when you take the derivative?
I completely forgot to do that. No.
No, you shouldn't use the quotient rule in the first place because you're using L'Hopital's rule.
Oh,
Huh?
are we not just doing L'Hopital?
Exactly.
Zero.
We are doing L'Hopital's rule. But then that'd mean that you're not doing the quotient rule on this quotient. Rather, you're just taking the derivative of the numerator by itself, the derivative of the denominator, and then evaluating that limit, right?
Yeah.
Go ahead and do that.